Hi there guys, just wanted to go through a quick example here on sketching using calculus to sketch a graph. So here's 4x cubed minus x to the 4. Now, so the basics here, we're going to want to find the stationary values, the turning points here. We're going to want to find the points of inflection here and understand a little bit about the shape of these things here. So let's, first of all, if we want to sketch this thing, it'd be great to be able to factorize it. So if I take out the highest common factor here, this now gives me a good idea of what the x-intercepts are going to be. So straight away I'm getting an idea here that it's going to go through when x equals 0 and when x is equal to 4. They're the only two x-intercepts. Now next to the 4 graph here, x to the 4, you could have something like that, or you could have something that goes the other way like that. Or you could have something that has a stationary point of inflection and then does something like that, or it could come from the other way around like this. There's all kinds of things that a next to the 4 graph could do. So let's use calculus to find out what this thing actually looks like. So stationary values. Y dash here is 12x squared minus 4x cubed. And of course the stationary values is when that is equal to 0, right? So common factor, 4x squared, 3 minus x equals 0. So therefore, we've got two stationary values, x equals 0 or 3. Now, often, again, they're going to want to ask you to find the coordinates, not just the x value. So when x is 0, chuck it back into here, and we get y is equal to 0. Or when x is equal to 3, chuck it back in here. So I put that in and you get 4 times 3 cubed minus 3 to the power of 4, and that gives you 27. Okay, so there's the stationary values of the function. Now, what kind of stationary values are these? Is it a maximum, minimum, or is it a point of inflection? All right, so a point of inflection is going to be when the second derivative is equal to 0, but not always. Let me take the example of y equals x to the 4. Now the derivative here is 4x cubed. That's obviously equal to 0 when x is equal to 0. And the second derivative is 12x squared, which is also 0 when x equals 0. So some people would say, well, if the second derivative is equal to 0, you've got a point of inflection. No, in this case here, if you were to draw y equals x to the 4, you just get a parabola that's kind of slightly more like that at the bottom, kind of flattened out at the bottom. That is not a point of inflection. X equals 0 right here is a minimum turning point. So not only does the second derivative have to equal 0 at the point we're talking about, which it does in this case, but also the concavity has to change. By concavity I mean it has to change from being concave down to concave up. So concave down to concave up, there we go, or concave up to concave down, this point right here. So both of those conditions need to be satisfied, okay, for this thing to work, for in other words to know that we've got a point of inflection. So let's get rid of all of that, get back to this problem. Okay, when is the second derivative here equal to 0? Well, the second derivative is going to be 24x minus 12x squared. When is that equal to 0? Again, I'm going to do some fancy factorising, which is not really fancy at all actually, but a bit of factorising. X equals 0 or 2. So again, 0, 0 or 2, if I get the point. Let's put 2 in here. Trusty calculator, 4 times 2 cubed, which is 4 times 8, minus 2 to the power of 4, which is 16, and that gives us 16. Okay, so let's see what we've got here. So already we've established that this point here is a stationary point. The second derivative is also equal to 0 at this point, so I'm guessing that this is going to be a stationary point of inflection. We've got this point here. We don't know if that's a maximum or minimum. I'm going to work that out. And it looks like this point here is going to be a point of inflection where the concavity changes. Okay, so what kind of stationary value do we have? There are two methods you can use to find out what kind of stationary value you have. Let's do it on this page. Okay, so Method number 1 is the second derivative test. If the second derivative is greater than 0, this means you've got a minimum value. If the second derivative at that point is less than 0, it means you've got a maximum value. The second derivative is equal to 0. This is the thing I've been talking about, a point of inflection. Normally. A few special cases, I've just given you one. And this one here might turn out that way as well. So that's the test you can do. So let's do it in this case here. The second derivative is 24x minus 12x squared. Okay, so 24x minus 12x squared when x is equal to 0 gives us 0, right? But we've already established that that point is a stationary value. Okay, so we get 0 for that one. 24x minus 12x squared, given that x is equal to, the stationary value was x equals 3. Given that x equals 3. Okay, so we're going to say y double dash 3, if you like, is, again, same thing, 24 times 3 minus 12 times 3 squared gives me negative 36. So it's less than 0. Therefore, 327 is a maximum turning point, or a local maximum turning point. You'll see what I mean when I get to the graph. Okay, so here's another way that you can work out what kind of turning, or what kind of stationary value you've got. Write them down on a little grid like there, 0 and 3, and then evaluate the derivative either side of there to see what's going on. So let's choose a value like negative 1, a value before 0, and see what's happening with the derivative. Remember, the derivative is way back up here, is this thing here. Okay, so I'm going to copy that. Let's chuck this down here. Okay, that's the thing that we're trying to evaluate. So when I put negative 1 in there, 12 times negative 1 squared is 12, minus 4 times negative 1 cubed is plus 4, so it's positive. So the slope of the curve there is positive. What's going on just after 0? So chuck in 1 there. 12 times 1 squared is 12 minus 4 times 1. It's also positive. So the curve's going to slope up. We know that it's 0 there, and it's also then sloping up again. So that clearly shows the shape of the curve and showing that that is a stationary point of inflection. Okay, what about 3? So if we chuck 3 in there, 12 times 3 squared minus 4 times 3 cubed, we get, 12 times 3 squared minus 4 times 3 cubed. We get 0. So we know that when x is equal to 3, we know it's going to be equal to 0. So what's happening at 4? What's going on at 4? 12 times 4 squared minus 4 times 4 cubed, negative 64. So it's sloping down. Okay, so this clearly shows kind of the shape of the graph, and it helps us to sketch it. So I'm going to put it all together now and see what's going on. So we've got, there's 0, there's 4, there's 3, and there's 2. So we've got a stationary point of inflection here. We've got, goes up, it's got a turning point there, and then it goes down like that. There we go. So the key features, stationary point of inflection there. We've got a change in concavity there. We've got the maximum turning point there at 327, and we've got the y-intercept there at 4. And that completes the sketch of the graph.